Hello students, this is the first of the two exercise set to supplementary exercise set from chapter 7, the power series method. I selected these two problems, problem 7 from section 7.2, and it's a differential equation problem. Solve this linear ordinary differential equation with variable coefficient using the power series expansion at t equals to 0. Second problem is a proof problem which has something to do with the analyticity. We're going to do this in a separate video. For now, let's focus upon the first problem. Okay, let's begin. How do we do this? The first step is rather obvious. We begin with a power series expansion at t equal to 0 as specified, and here it is. Y of t is equal to summation n is running from 0 to infinity, cn t to the nth power. And then what do? We simply take the derivative of each term, like this. N comes out as coefficient, and subtracting 1 from the power, we get the second term. Let's do the color coding here. This is going to be red, and this is blue. And the second derivative is going to be green. And let's go over there. Same thing, take the derivative once again, and this is what we get. N minus 1 comes out as coefficient, and subtracting 1 further, and we have n minus second power. So we're going to put these three into the original equation. Y double prime, green, Y prime, red, and finally Y, blue. Okay, we need a bit of algebraic manipulation here. Number one, let's break up this parenthesis. Distribute t, and then -1. We get these two series. And then the other two series stay the same. Final manipulation. Let's remove this t. Multiply this t to each term. What do we get? We have n minus first power. Let's do the same thing here. Multiply this t to each of these, and we get nth power. So that is the conclusion from step 1. Okay, let's go over to step 2. And the very first line of step 2 is just a reproduction of the previous, except that I disabled all the colors because I don't need those anymore. Okay, all right. And let's work out these series. You see, first two series are a bit problematic because we have t to the n minus first power and n minus second power. The other two are okay. We have nth power and then another nth power. So we have to do some index shifting so that everything becomes t to the nth power. So let's begin. And then let's begin with a new set of color coding. Let's begin with blue. And then let's use another color, red here. And okay, all right. Let's keep this in green. And one more color, brown. And if you do it right, you're going to get the second line. But I guess we're going to need a bit further explanation here. So let's talk about it. Where is brown, by the way? Okay, I found it. Okay, all right. Let's expand the font a little bit. Now, how does the first line, which is actually the conclusion of step 1, became the third line? Let's work it out from this intermediate step. So I just copied and pasted the same thing down here. And green and brown series, they're okay. They already have t to the nth power. No problem there. How about this one here? Well, let's work it out. I need nth power here, but I have n minus second power. So what do? Replace this n by n plus 2. we do the same thing here. All n becomes n plus 2. And this becomes n plus 2 as well. And that too. Now, do you see this red series is the same as this red series here? Do you see? This n comes from n plus 2 minus 2. And n plus 2, these two are the same. And then let's see, n plus 2 minus 1, that's the same as n plus 1. Here's n plus 2, the same thing. Finally, this n plus 2 is equal to 2. Manipulate it so that n equals to 0. Subtracting 2 from each side of the equality, we get that. Let's do the same thing to the blue series. Now, I want this n become n plus 1 so that the total becomes n plus 1 minus 1 so that we get nth power. So I just replace this n by n plus 1, so we have to do the same thing to everything here. Okay, I did it. So n equals to 2. We have n plus 1 is equal to 2. This n became n plus 1. This n became n plus 1. And here, Cn became Cn plus 1. And this n also became n plus 1. Now, do you have simplification? T to the n plus 1 minus 1 power become t to the nth power. Fine. Cn plus 1 will get as Cn plus 1. And n plus 1 minus 1, that's the same as this n. And this n plus 1, same here, just n plus 1. One final step. Here, n plus 1 is equal to 2. Subtracting 1 from both sides, we get n equals to 1. That's where we start. So what did you get? This original blue series, via this index shifting, we ended up with this blue series. This red series, using this index shifting, we got this red series. Green and brown remain the same because they already have t to the nth power. Okay, we're almost there. We don't need this extra step here for now, so let's hide it. And let's go from here. Now, t to the nth power, that's all good. But let's look at the starting point of these series. Begin from n equals to 0. This begin from n equals to 1. Start from n equals to 0. Start from n equals to 1. They're not even, so we need some further work. How do we do that? Easy. Around regular singular point, we don't really need anything spectacular because when n is equal to 0, what is this? That's 0. So we just added 0 to this original blue series by starting n equals to 0. Adding 0 doesn't change anything, so this blue series and the next blue series are the same. How about this red? I didn't change anything, so of course they're the same. And let's look at this green. Are they the same? Yes, indeed. I changed the starting point from n equals to 1 to n equals to 0, but when n equals to 0, what do you get? It's 0 times the C0 t to the 0 power. That's 0, so adding 0 doesn't change anything. So this green series and that green series differ by 0, so they're the same. And finally, this one, I didn't change anything, so they have to be the same. Where's brown? Okay, all right. Now, okay, all the summation and t to the nth power are the same. So the summation and t to the nth power are the same, and get all those coefficients together. This came from the blue series, and this came from the red series. This came from green, and finally this came from the brown series. We have to have 0 for arbitrary t value, always 0, which means this coefficient has to be 0, and that gave us this recursive equation. One final color coding here, that's blue. and red. And then this green and brown, put together we get this. Let's keep it at black. Okay, final step. Let's solve for c of n plus 2. That's the latest term. So you can solve it with respect to the two previous terms algebraically like this. And there goes my recursive equation. How do we deal with this recursive equation? Let's discuss it in a separate video. For now, let's stop here.